going? I'm Sam. I'm from Twitter. I'm going to talk about Summingbird. Before I do it, I have to show you guys this. I had worked on this library called Bijection for a while, and so that's it. That's my talk. We've committed a lot of sins in the Scala community. Yet another one was, this is how we were doing macros with like auto-generated injections. It's terrible. I'm very, very happy that we have like a real way to do it now. We were just sort of building like Scala scripts that were auto-genning code. This is not the way to do it. So Summingbird. So as I said, I'm Sam. I work at Twitter. I work on the analytics infrastructure team. We use a lot of Scala, and I'm going to talk today about Summingbird, which is a library we've been developing for, I guess, a little over a year now, which represents my thoughts and kind of my group's thoughts on streaming analytics at large scale, and I guess trying to solve the fourth bullet point that Charles had of that, there's a lot of sort of nice things you can do in languages like R and Python and all this, but when it comes to production, like often it's just a big splash of question marks. So how can we use a language like Scala to kind of allow big MapReduce jobs to run, but give the power back to the user to make these things easy to write? So Summingbird, it's an open source project that a lot of the stuff we've built during this process has been open sourced as of September, so you can play around with it. Just background, it was primarily the work of myself, Oscar Boykin, who's been done some talks to the Scala community, and then Ashu, who ended up doing, I have to mention his name, he did a lot of the work at Twitter to kind of productionize this stuff and really get like some ass-kicking applications out in the face of some of the fear of Scala that existed in like a Ruby and a Java shop. So kudos to him. So what I'm going to talk about today is what Summingbird is and what kinds of streaming MapReduce calculations it lets us do, even what I mean by streaming MapReduce, like what kinds of things does this library let you do in Scala. We're going to talk about this Algebird library and kind of how like abstract algebra and analytics fit together. And I know we kind of get trolled at work about this, but I think it's an extremely powerful combination. We're going to talk about how our use of some of the abstract algebra stuff really puts the compiler to work when you're writing analytics applications. We're going to talk about the special thing you can do with Summingbird, which is to run your analytics logic in a batch mode on Hadoop and then kind of in a real-time system and merge these things together in a client. Basically like real-timifying Hadoop. That's a thing that falls out of the Algebird uses we've done. And then we'll look at a few example applications of like how we're using Scala at Twitter at scale. So the vision of this project when we started, again, analytics infrastructure group, we're trying to enable analytics. The background on the kinds of analytics we need to be able to handle, Twitter's got a shit ton of data, like a lot of data. And at some point, like I'd done work before in Python and R, and you can write really, really expressive things in an Excel spreadsheet, say, but it's hard to take them to production. At the end of the day, you need to be running these things on, 20,000 tweets a second. And maybe that's not like a common problem, but it's certainly a problem that I hope we all run into, as we are not frightened by these sorts of big jumps that have to happen when you hit scale. So we get a lot of tweets, and we have a lot of like big Hadoop clusters that we're pretty committed to. Twitter's a Hadoop shop, and as a result, a lot of our analytics just aren't real-time, which is like kind of sad because Twitter's the real-time company, but a lot of our dashboards for a long time were sort of delayed by 3 or 4 hours as these big Hadoop jobs had to jump along. So as our analytics like data scientists wanted to start playing with real-time systems like Storm or Akka, we had to address this problem of like, we've got a lot of infrastructure that's already built on Hadoop. How do we let people get the real-time benefits, but not have to go start everything from scratch, which is a pain in the ass. Systems problems are horrible. A lot of the issues that come at scale involve like serialization and just which database you're going to use. All these things we were solving over and over for each application. We wanted to solve them one time and be able to take a user's logic and go apply whatever systems optimizations to that logic. Auto-tuning of our real-time stuff, whatever. We didn't want to have to do it over and over again. And finally, and this is the one we were most excited about, we wanted to make like non-trivial real-time aggregations as accessible. I say as scalding here, but whatever. Just we wanted to make them as easy as like doing like a sum in Excel of a spreadsheet. And what we found, I guess, is a lot of the applications people were building basically were just counts. And, I think that comes from, like, it's inherently just this sort of uncreative way to look at data. Once you hit the scale issues, there are a lot of certain things go off limits, like you're not able to use certain data structures or operations. A lot of iteration becomes difficult. And if you don't have these like solid constraints on what kinds of things you can do, it just gets really like fuzzy. And so you kind of devolve to just doing counts. And I don't know, like we wanted that not to be the case. We wanted to give people strong rules on what we'd allow in our system and let them play freely within those bounds. And that's, later, this is sort of a foreshadowing of abstract algebra riding in to save the day, as it so often does. In relationships and coding, it's, I found it accessible in all areas of life. So what do we make? What is Summingbird? Summingbird is a declarative MapReduce DSL. It's basically like, you can think of it, you write what look like Scala collection transformations. What's really happening is you're writing in this sort of builder API, which is building up a DAG of computations. Nothing's happening. You're sort of working within this. It's not really a monad, but I have to say it. And you're handing this thing off at the end of the day. That's what your data scientist writes. They hand it off to an executor, or a platform, we call it, that will fire up that MapReduce job in the system of your choice. So we currently have a Storm in Hadoop. One of our guys over the weekend jammed together an akka platform. That's actually like really, really promising. We also have a client that can consume the data produced by Hadoop in its sort of offline, transactional mode, and Storm in this real-time mode, merge these results together and give you what looks like a real-time client that's like mostly backed by Hadoop. So like quickly, probably everybody knows what Hadoop is. Do you guys know what Storm is? Okay, so it's like quick background on what I'm talking about here. Probably should go with that. Hadoop is like the MapReduce model where your data just exists like in some sort of distributed file system. You go read in big chunks of this data, process it, and then output some next process. So if you want to go do like build dashboards, you've got some sort of architecture which is like consuming, processing, writing, consuming, and just kind of iterating over and over. Storm is a way of building up like a real-time version of basically like a stream processing flow that sticks together like functions and queues. So instead of reading off a disk, you're reading off of a queue coming in. It's sort of logically identical to the Hadoop case, but the systems issues are very different. So we wanted people to be able to like give us their code, and we just run it on both, and they don't think about it. So it looks like, we've got sort of these operations that look like Scala collection operations. You're flat mapping, you're filtering, you're doing all this. Really, you're just building up a graph, as I said. And at the end of the line, like typically you're writing into a key value store and performing some aggregation, or you're like kicking off to another queue or something, which can be used as a source by someone else. So this is kind of what all the jobs look like. I'll give you this framework. This is MapReduce. What all of these jobs look like, the kind of analytics workflows I'm talking about, and I'll try to convince you as we go on that many, many, many of the analytics operations you like to do like fit into this model. Some event stream exists. It's kicking out tweets, say. You do some sort of flat map transformation. You either, for each item, for each tweet, you either like emit 0 or more things, as flat map does. And then at the end of the day, you end up with key value pairs. And what a MapReduce system will do is like group by the key, give you a list of all the values that are associated with that key. What Summingbird does is uses some sort of associative addition operation to like add them all together. So if you want to count tweets that contain some URL, your key value pairs would be like a key and a count of 1. And then what these reducers are doing is like getting for every key a list of 1s and just adding all the numbers together. So your database, when you go to build your dashboard, looks up the URLs and it gets back like a count that in real time is just sort of ticking every time you query. And that's again what all these jobs look like. In offline or in online, the systems issues are different, but what I mean by streaming MapReduce is that you have to think of this as like being able to accommodate one item at a time. Like forget Hadoop that you can process a bunch of things and like do big joins. Imagine one tweet comes through, you pull out its count, and you add it into the data store, and you've just sort of ticked that one counter, you're good to go. My buddy Oscar jokes that the MapReduce paper should have been like the flat map shuffle paper, because like the map of MapReduce is actually flat map, and there's no reduce. That's just a function, and not a good sales pitch. But so the flat map shuffle architecture, out of flat map, as you know, you can build map by omitting one thing, and filter is just apply a predicate and either omit the thing or don't. So this gives us kind of our stream transformations. The remaining pieces that let Summingbird build up these sort of massive data graphs are, there are 2 ways to input data and 2 ways to output data. This is just background. We're going to dive into the store implementation, but I want to just give you the sort of vision of Narnia that we're trying to get to. Sources is the data stream. These are like the 4 abstractions you have to define something that can execute a Summingbird job. A service would be like some key value store you can perform lookups on. A store is something you aggregate into, like we just looked at. And a sink would be, as your stream's going, you just sort of tee items off into maybe another queue that can be used as a source. So what we have at Twitter, the way we've kind of used these concepts is we define like all the incoming client events, like the tweets and the social events and all that, as sources. Whenever someone writes a new Summingbird job, their outputs get registered as new inputs for other people to consume. So we've got this sort of data catalog of, okay, you generated like, the top K, URLs that are tweeted per day. Someone else can go do lookups on that. Totally fine. And you just sort of are expanding this thing out. So you have these constraints of you have the key value model, but we're trying to sort of leverage that and give you these big tools. They all start with S. Amazing. This is the thing I'm most proud of in Summingbird. Yeah, this is what we call a tight abstraction, folks. So you see how we do our design. Okay, so this is sort of like Summingbird for me was like my journey into Scala and the community, and I learned a lot in the process. One of the early realizations we made that kicked off this Algebird library, we were trying to think of like, okay, you've got a key value store. Like, what kind of constraints can you put on the value in this equation? Like, what can I store in Memcache or Redis or, what kinds of things like work for doing the reduce of MapReduce? And what we realized after Oscar sort of pontificated for a while about it was the monoid trait is enough. This sort of generalization of addition was enough of a constraint that if you knew that your value type had this monoid, if you could write a monoid instance for it, boom, you're good to go. Like any of our data stores could go handle that particular value type, provided and this is where the bijection thing came in, that you could serialize it, but we'll just talk about the monoid for now. So yeah, all this is, how many people are familiar with this idea? Okay, awesome. This is so good. This is why it's so good to speak at a Scala conference. Because I coded Clojure for a long time, and you try to talk to people about this, and I've had people really because they think it's a monad, and it's, I don't know. There's a lot of, I feel at home. So the monoid is fantastic. Once we sort of saw this, the challenge for us became oh my God, if we just go define a grab bag of data structures that implement this, that becomes it's like a multiple choice test for analytics. It's what do I want to do? Oh, okay, I'll just go look at this sort of list of data structures. They all can work. It's a different way, I think, of thinking about the sorts of operations you want to do, but it turned out to be immensely powerful. Spire obviously has the same type class. The only reason we haven't switched over to Spire, I'll say it to you guys publicly, is Twitter's stuck on Scala 2.9. So we can't do all the cool shit we've been talking about. But
yeah, we're gonna backwards to 2.9. It's gonna be great.
Really? Yeah. Awesome. Okay, I'm glad we could pull you guys into the past where we live. So yeah, so we released this library called Algebird, which you may have seen. It's got a ton of, I would say Algebird's difference from Spire would be that we were focused on the data structures that implemented these things. Keltman Sketch, which we'll talk about. We have a lot of these approximate data structures, as well as just default implementations of the monoid on numbers would be addition. The monoid on sets is set union. We use the 0 to go filter out values from our data stores. Anyway, so Twitter, as I said, was doing a lot of Ruby and JavaScript and kind of was in Scala, but our group wasn't. So we're monoids is amazing. I felt like a cat with lasers coming out of my eyes. We're walking around preaching to people about this abstract algebra, and the response is sort of the I mean, this was early days, verbatim, as you know. But people have come around, and I had a guy say to me last week, because we use a lot of implicit resolution to compose these things, and we'll go into that. I gave him, his eyes were getting wider and wider, so I sort of walked him through this like default implicit resolution I want him to build, and he's like, "This isn't programming. This is sorcery." I think it's good. I think that's a good response. So Summingbird, I guess in a line, would be like a way to run Algebird at scale. Like take the Algebird data structures and forget the execution platform. You can do this at any scale possible. And the other kind of lesson from that realization was start with the data structures. So yeah, as I said, that's the difference with Spire. Like we want to pull those things in because there's this interesting observation that by giving us sort of the algebraic properties of your value types, for every algebraic property like associativity, or you've got a monoid, you've got a group, there's a set of optimizations that we can do at the system level. And so the API design trick with Summingbird was to have, like, how can people tell us what it is about their values that exist, and then, you know, select from our set of optimizations what they want to apply. That's kind of like the story of what we're working on now, but we'll keep going. Again, another sort of tale of this was a lot of people say, like, oh, the type system's so nice, you won't have runtime errors. And like coming from Clojure, I worked on like Clojure map reduced systems for a while. It's a huge win. It's still kind of a pain in the ass. So what we wanted to do to mitigate that was like, we were trying to figure out basically in this process of how we could use the compiler to do a lot of work for people. Again, like you note these algebraic properties, you've got a monoid, we fill in a lot of boilerplate for you. I think the macro story is you know, solves that a lot. One example of that was using implicit parameters for monoid composition. So if you wanted to build, say, analytics, and this is like pretty common, of just like views per URL tweeted, you could consume tweets and kick out key value pairs of like URL to count, right? So that's straightforward. There's a default monoid on integers. This will just work, and no problem. What if you wanted to count unique users? Well, you'd kick out maybe a set of user IDs, and then at the end of the day, you'd query the size of the set, but there's a monoid on that too. You just take the union. What if you want to do both? Like, is that okay? And it turns out it's totally fine because pairs have a monoid as well, which is just a pairwise sort of combine things. You know, you might want also like the top K users, as well as the succinct users and the total users. So being able to look at your aggregations and just layer these things up when at the end of the user's not doing anything here because all these monoids are defined implicitly, like looking into this grab bag and building dashboards that way has turned out to be like at least an answer to why isn't this as easy to use as Excel? Is the production story is solved and we can still do a lot of that production work for you. So we're trying to kind of come in from the other side. Associativity, also huge. That's kind of like, you know, the property that has to be true for a data structure to have a monoid. The combination has to be associative. Once you know that you can associatively combine, you can parallelize these things and turn them into Lisp. And, and that, you know. So this is a good story. Okay, so the other thing that the monoid let us do, it just sort of fell out of the works, which is wonderful, is this combination of like batch and real-time output. So are you guys familiar with this? Nathan Mars has been speaking about this idea of like the Lambda architecture, like this kind of way of, okay, so as I said, we're a big Hadoop shop, like most of our pipelines are in Hadoop. It's not real-time. The problem we wanted to address with this, we hoped we could address, was how do you take like a batch pipeline, or really like a pipeline in whatever system you happen to be using, and add the real-time component to it without sacrificing all the work you've already done. So one way to do that is serve most of your data out of Hadoop and then take only like real-time to whenever Hadoop has caught up, take that last little piece and fill it in with a real-time system. So you're computing sort of in double. Storm's computing, Scalding's computing, or Hadoop's computing, and then the client at the end of the day knows how to add these things together with a monoid. So the client can sort of participate in these things as well. So this is, I don't know if you'll be able to hear me, but I have a pointer. So the way these systems work at Twitter, the way we've deployed Summingbird, and again, this is all open source, is our logs come in, they pool up in these green circles, and all of that gets absorbed or sucked in, like built into key value pairs and aggregated into a Hadoop data set, which has a strong sort of top cutoff at this notion of a batch. So a batch is like a window of time, right? So we will say like, okay, my Hadoop run when it went from all the data in Hadoop is from the beginning of time to like the end of batch 0, which might be like Wednesday at midnight. If it's actually Wednesday at 3 a.m., when my client goes to query, I'm missing 3 hours of data. So the client will know, okay, go get what you can from Hadoop, and then at the same time, these logs are being sent down a real-time queue and processed into these partitioned buckets by a real-time system, hopefully akka within a week or two. So the client will know, like, go to Hadoop, get the latest stuff, and then go fill in piecemeal the remaining batches from Storm. So again, like the problem with a real-time system is that it just has it's lossy. Errors can come into play. Like it's harder to reason about a real-time system than it is about Hadoop. So we solved that issue by just not worrying about it and saying shit doesn't really go wrong in real time, and if it does, when the next batch of logs shows up, Hadoop will fire up, chunk forward, carry along all of its data from before, only merge in the deltas, and then the client will hit this batch instead, and this will just sort of drop out. It'll never get queried by the client. So this sort of marching thing has been very, very useful. One, for just, again, like serving most of our stuff out of rock-solid Hadoop, so errors are bounded. Two, doing backfills is like amazing. You know, we can just go ahead and start up a second Hadoop process that goes from the beginning of time and filters out like maybe 80% of your clicks on tweets are bots. It's unclear. If you have to do extra filtering, no problem. And we can have, you can imagine many levels of this where, say, Akka's doing one, and sort of levels of real-time or accuracy in your machine learning application. Like if you let Hadoop kind of take a long time and do the right thing versus having something else do kind of a shitty job and being available fast, what Summingbird is built for is to execute different pieces in different spots and let you sum them together at the end of the day. Is that clear how that sort of batch real-time thing's happening? And like it seems like a pain in the ass, but this is a systems problem that the user doesn't have to know about. So like systems guys take this, and it's been wonderful. And this is what I said. Oh, okay. So that's what we built. Now let's talk like example applications. This moment was made possible by Summingbird. Not this one, the bottom one. So yeah, one analytics product that actually like an intern came to us with, and we were looking for like an intern to work with us because they weren't interns. The idea was weren't as scared of Scala and didn't have emails to answer and etc. This guy came to us with the idea of what happens when you embed tweets on websites like this. There's a lot of sort of news context around this. If I go embed this in New York Times, there are stories written about these tweets. What if you could, when a tweet was embedded like this, we have a stream of all the impressions happening to that tweet. What if when someone looked at the bottom of that tweet, they could see every headline, sort of backlinks to news headlines that had embedded those tweets? So this was like perfect for Summingbird. We've got our stream. All we had to do was imagine the key value pairs. You can do this, I guess, with a hash map value. Like the data structure, or the requirements, I guess, were for every tweet ID, if I look up a tweet ID, I need to get back like something like a map of URL to number of impressions. And like, maybe I don't care about all the values, like only the top 10 or the top 15 or so. Additionally, like it really only matters what the ranking is. Like it doesn't really matter what the exact values are. So I don't know. This is like exactly the description of a count-min sketch, which we'll talk about. It's a particular type of approximate data structure. So we sort of freaked out. We're like, you have to use this. Frightening the intern. But we managed to write this code in an afternoon that we'll go over. That would be enough to build the feature. It would be wonderful if it were real time. Adding that later would not be such a problem. So how many of you guys are familiar with the count-min sketch data structure? Okay, awesome. So like, you guys can tell me if I fuck this up. Anyway, it's a pretty simple data structure at the end of the day. What this is a way of building an approximate map. So a way of like, if you want to keep key value pairs or the values of some sort of count, but you can't have it grow. Twitter has a problem with skew, where like maybe 100,000 news articles embed some tweet. and then your value gets so big it can't fit in memcache. And like these are just the things that I worry about at night when I'm home drinking. So this stops that. This is, I allocate a 2D array, and every time a key value pair comes in, I hash k down, turn it to a byte array, hash it, and or hash it actually like d times, I guess in this case, and I take take the value and I add it into the buckets that have been pointed to by each of those hash functions, mod the number of columns that I have. So you're going to end up with some entry on every row. You might have clashes in value, but the idea here is that for every value you take and you add this thing into one of these cells. So these cells are holding, in this case, in the simple case, like integers or longs. In the more general case, anything that you can add. So like kind of like something with a monoid or a semigroup. When you do a lookup, you go ahead and you take your key, you hash it to all these buckets, and you go read out of every single one. And because you've got a fixed space, you're going to have collisions. But what you can say is that the minimum of all the things you've read is the spot with the least number of collisions that have happened. So if every key, whatever value, I've added that many to all these spots, whatever's least likely to have been hit, I can call my upper limit on my value. So there's going to be, for every key value pair, for every count that's in this map, there's going to be some error, but it turns out I can bound that error, and the error gets smaller as I allocate kind of like more and more landscape to this 2D, to this matrix. So that's how it's built, and you can reason about the error here. And in this case, and the other thing you can do is just keep like along the side a top K bucket where you say like, okay, give me the top 10 or top 20. And every time you add, just look and see if something has been promoted into the top K or kicked out. So this data structure is like perfect for this. You can get a little crazier by like for small maps, only keeping the map and sort of promoting it up to a count-min sketch as you get bigger and bigger. But again, like that's just monoid composition. It's perfect, just a systems issue. So yeah, same picture we had before, only one data source, and we're kicking out a map. Like I said, tweet ID, count-min sketch map of URL to long. We group by tweet ID and just add these things with the count-min sketch monoid. The monoid is just take the matrices and add all the values together at the same locations, as if you sort of added all the values from the right into the left very, very fast. No problem. Okay, this is what it looks like. This is what the first draft looked like. Most of this code is like converting from Java thrift to Scala thrift, which is like the true nightmare of what we're doing. So, but you can see like if you look closely up there, source.filter, just filter out the events we don't care about. Here are the key value pairs we want. They're also generating, by the way, like the top tweets per hour, per day, per time bucket by this ranking, like how many people have been embedded the most. And it's like a badass dashboard. Like I hope we release it, but if we don't, like you guys should copy it because it's so easy and it's awesome. Just, when big events happen, like this dashboard gets updated the most. It's like the most important tweets of all time dashboard, I guess. And then some by key into the store, and here we're like setting the monoid. We haven't come up, like, when we switch over to Spire, you guys will have solved the problem of marking whether a monoid's commutative, all these things. We don't have to solve the design issues. But this builds up a data structure that you give to Storm or Scalding, and it just executes. No problem. Yeah, I explained it. We also run, I can't show you this, I guess, so maybe it's not real, but we run all of our advertising dashboards. This was kind of the first production application, is we switched over to this system to run whenever someone advertises on Twitter, they get all these metrics about the people who are consuming their stuff. That switched over early, and it was this enormous win, and maybe a 5x speed increase, just from delegating out the services to folks who knew what they were doing. Hadoop team ran the Hadoop job. Storm team ran the Storm job. And the client, most of the data is getting served out of memory, or like memory that caches down to SSDs, because we can do most of it out of big read-only databases. No problem. It looks like we're going to be able to start, not promising, but like the question has been like, how would you do analytics for every user on Twitter? And it looks like these approximate data structures provide the answer. Like Oscar sort of is now pontificating about like a multi-terabyte count-min sketch. It's just the biggest count-min sketch the world's ever seen. Like, that's the answer. So you all have a place in this count-min sketch. So next, the big thing we want to do is an ACA platform. I guess the biggest pain in the ass now with all this is we kind of solve the systems issues, but storm topologies, you fix these things up and they can't auto-scale. And we have these huge bursts of traffic. An ACA planner would let our topologies sort of sample and scale dynamically, and at least that's kind of the belief, and that's sort of where we're moving to. More data structures. As Algebird sort of fleshes out, our ability to go pick these things out is better and better. And then what we're working on now is sort of a pluggable like graph optimization layer where we can do filter pushdown and predicate adjustment and all this on the logical plan without having to care at all about scalding or storm or any of these things. Auto-tuning, the real answer for this is just ACA. Like that's what we're going to do. Yeah, it's open source, so if you want to watch us develop, great, but I guess we're trying to sort of kick out as much as we can. It's a big system, but the pieces are coming together for, being able to just like one-stop run this thing. So I guess quick summary. The takeaway that we had internally is it's a constrained system. A lot of the feedback we got was like, what if I don't have a monoid? What if I want to add 2 different types? What if I want to do something that's not MapReduce? The answer was, fuck you guys. You can't. But it turned out that like it didn't matter because like most of the situations people were coming up with, and this is either just like stunted creativity or what, but it was very hard to come up with something that was like outside the paradigm for most of the stuff we wanted to build. Obviously there are things that aren't MapReduce. Well, there aren't. You just like stick everything in the reducer and like do whatever. But it was appropriate for most of the real-time stuff we wanted to do. We have so many projects that are so exciting that it fit the model. 2, it's all about the algebra. Use Spire, use Algebird. Don't be afraid. Just embrace it. And like harness the compiler. And I think that's, these things are painful, but telling the compiler about these things, a lot of the macro stuff we've seen is very, very exciting. And the big one for us is, we say data scientists, but folks who like don't want to deal with systems issues, like frankly me, can go run real-time systems and not have to go learn a whole new set of paradigms. So that's what I got. Here's our URL, and there's my Twitter handle. But yeah, that's Summingbird. No, it's going to happen. I can't wait for it to happen. No, he's not there. Storm, okay. Like a lot of the stuff in Storm that's exciting about like exactly once semantics. This word semantics, like I don't know. A lot of these like features that Storm has that are very, very powerful, like the Trident abstraction and all this, are there because if you're running a fully real-time pipeline, like that's holding years and years of data eventually, like you want to limit error as much as possible. And it's very, very hard, like I've found, to tweak the systems separate of the logic if you want to run only real time. So by like restricting our real-time systems to only 2 or 3 hours of serving and serving most of our stuff out of Hadoop, we've kind of accepted the payoff there of keeps the Storm topology simple, so simple that we don't use any of the advanced stuff. And, if things go wrong, like that's fine. Because they don't really go that badly. So yeah, I think like, again, the ACA promise of auto-scaling, or maybe I'm just kind of blowing it up in my mind about how wonderful it could be, but dynamically adjusting topology settings, ACA seems to be there, and I would love to at least experiment with that migration. And the story here, by the way, isn't about like we can kick out Storm or we can kick out Hadoop. It's like, it's not that choice anymore. We can go play with Spark, and we can go play with ACA, and it's different applications can pick different things, and we don't become like a Hadoop shop anymore. We're just like an analytics shop.
You talked about basically it sounded like pushing filters down the tree or rewriting this tree sort of before it gets to Hadoop or before it gets to Spark or Storm or whatever. Can you speak a little bit more about either what you've done in that or kind of what you're looking at? I mean, this sounds very interesting.
Yeah, sure. Like, okay, one example is a basic one that we've done is our Storm topologies, rather than if you've got multiple flat map stages after each other, we can consolidate those down and not have sort of extra serialization jumps. The big one we're working on now is if you have sources or flat maps that kick out options, so some sort of mapping or filtering, or like filters right after a join, we have these there's a project called Parquet going on at Twitter where it's a columnar format for Hadoop, where if a filter is near the source, you can jam all this stuff down into the data itself and like never read it at all. So being able to say like, okay, here is the like filter push down, you then present the compiler at this stage with like a list of a source and then a list of filters that have happened right afterward, and it can do what it wants with them. So it's pretty primitive now, but I don't know of any other libraries that are really working on like pluggable graph optimizations with like only the graph, rather than saying like this is the pig optimizer or this is whatever. So yeah, the big one is like flat map squashing and like minimizing jumps within Storm across processes, and then also like filter push down so we don't have to read a bunch of data, which is the huge win. Yep. Oh God. Honestly, probably like January, February. But whatever, I don't know. It's not hard. You know, most of the external stuff we pull in. Okay, the quick story is like all the stuff we pull in from outside are like these libraries Oscar and I have written. So like they're all 210 ready. All the Summingbird's 210 ready. It's good to go. We don't use it. The only thing this is holding us back from is like fully migrating over and writing a bunch of macros, for better or for worse. And then as a Lisp guy, like I'm excited. And then also getting our future APIs. Like a lot of our stuff exposes Twitter util stuff, and it should just be in terms of Scala code. You know, a lot of our stuff's on Maven, and it's just like a horrible migration process. But all these libraries are 210 ready. So if you want to use them, please go ahead and like drag us into the future. Yeah?
Have you heard of skeletal programming?
Skeletal programming.
It's an interesting approach where you basically, there are parts of your algorithm that are sort of well-known prototypical operations like count, min, sum, that kind of thing.
Mm-hmm.
And you can kind of arrange things into what they call muscles and bones. And the bones are the parts that are sort of well-understood algebraic properties and also well-understood parallel properties.
Mm-hmm.
And then the muscles are the parts that you have to write. And then if you can kind of categorize them or characterize them as having certain properties, then you can sort of build an optimization of the algorithm.
I mean, that sounds exactly like what we're looking for. An example of where knowing more and more about the data structures is important is like, we were talking about this earlier, if we knew that you had a group and you could subtract your data structures, instead of outputting just aggregations, you could output like aggregations in specific time windows and do very easy range queries by just like doing 2 lookups and subtracting, rather than pre-aggregating like hours and days and months and all this. Just have your store accept a little more storage and range queries wherever, you know. So yeah, I'll look into that. Damn, it's a great name too.
Unfortunately, the only Java implementation I've seen is GPL.
Okay.
Which is a bit of a problem.
All right, yeah. Cascading was for a long time. I don't know. It's like, it's server code. Maybe it doesn't matter. But it matters. Yeah?
So if you've got sort of Hadoop set up and Storm set up, how much extra like kind of infrastructure stuff is over Summingbird? Or is it just, you just put it up and then you're happy?
So the method on the platform, other than like, when you implement the planner, the sort of, and then there's a plan method on it. And so it kicks out like a Storm topology instance or in Scalding like a type pipe. So we've tried to keep it slim in that if there are things that, like, there's obviously tuning and configuration and things like this for your system that we don't want to go to get like the covering set of all those. So say you wanted to use Spark's ability to iterate really quickly. You could take your ETL pipeline and like implement that in Summingbird and then just kick out to Spark and, you know, jump back to Spark's primitives. So I think, does that answer the question? Okay. Yeah. Like we tried originally to cover everything and it was just, we had like, okay, let's create like yet a new config and everyone can have a bijection over to that and like, it'll be great, but it's a pain in the ass. Yeah.
Yeah, what do you guys use to manage what things you could do with new metrics that you're adding, whether you can group it or how you combine different functions together?
Do you mean in terms of like output from this stuff?
Well, as clients are using the values that are stored and want to combine them in new different ways,
Sure.
how do you restrict what operations you can do?
Yeah, so we part of like the sort of glut of code that we kicked out was this library called Storehouse, which is a key value store abstraction which plays well with the monoids and also with the serialization that we use in Summingbird. Like often you write these things and you kind of forget about the client. Like you analyze the data, you kicked it out, and like someone else can figure out how to read it. But with this, a lot of our work was, okay, Storm will write data using this injection, and then the key value store can read it using this one. So you end up with the same values that you aggregated on the other side, and you can sort of continue to build using the monoids and the functional transformations and things like that. So the merge between the batch and the real time in our case jumps you over to the client, and then you're just building on this key value store. Does that answer the question? Yeah.
So if someone wants to play with Summingbird but doesn't have like an ops team at their beck and call, is there like a toy backend you can easily use to just like do tests and stuff with it?
Yep, there's an in-memory implementation, which is kind of a toy. And yeah, and the Storm one you can get running on your local machine, but again, like it's kind of a pain in the ass. There is an in-memory one, and basically instead of like Storm queues, it just uses streams. So you pass it streams, you do the transformations, and you plan it out to a new stream that has done all the stuff. So that's good to go. We wanted to do one on top of Finagle and have like a future-based thing where you end up with like a future and you can, fulfill promises. But yeah, play with that. The way I would see this being used, I guess, like if I were picking this up is if I wanted to do analytics but knew that eventually, like I hoped I was going to do Hadoop or Storm, but didn't want to make that decision now, I would use the memory planner. And just know that like, okay, if I stick to these guidelines, hopefully I get a lot of help from the algebraic data structures, and down the road, I can just redefine my sources and be good to go.
We need to cut it off.
Oh yeah? Okay.